Let's talk about polyatomic ionic compounds. Once again, if you are dealing with an ionic compound, you're going to have a cation and you're going to have an anion, meaning that something will have to have a positive charge, something will have to have a negative charge. And as I mentioned in the previous video, sometimes the cation will, instead of being a metal, it might be NH4. And now what's going to happen is that the anion, though, as opposed to being a single element like it was in the case of the binary compounds, the anion can now be a polyatomic entity, meaning that you have more than one element. In fact, in particular, you're going to have two elements, and one of them is going to be oxygen by default. Alright, so what happens here is that we're going to use the same table that we used before when we were naming the oxyacids, with one little addendum, and that is that instead of ending the end with ic acid, we now end it with ate. And instead of ending the ending of the molecule with ose acid, we will now end it with ite. Now the table here stands for just the name of the anion. You will still have to name the cation separately, followed by the name of the anion. So this table right here is only meant to help you with the name of the anion. Alright, and so we talked about the second row elements that contain a maximum number of oxygens being equal to 3. The charge of the anion is going to be group number minus 6. And if you look carefully, you realize that this formula is exactly the same one that we had before for determining the number of hydrogens, except that it's backwards. Before it was 6 minus group number, now it's group number minus 6. And that will basically ensure that you end up with a negative charge for your anion, as you well should, since anions need to be negative. Alright, so looking at the second row and the second row only, for the central element, we're talking about boron, carbon, and nitrogen in groups 3, 4, and 7 respectively. If you look at the charge of the anion, now starting with group 3, 3 minus 6 will tell you that the charge of the anion has to be 3 minus. The maximum number of oxygens ought to be 3. And for group 3, the element in question will have to be boron. So we're dealing with BO3 with a 3 minus charge. If you deal with a group 4 element like carbon, the charge will have to be 4 minus 6, or in other words, negative 2. And the group 5 will have to be 5 minus 6, or negative 1. And so the maximum number of oxygens being 3 in each one of them, this is how you find the charges: 3 minus, 2 minus, 1 minus. And then since that's the maximum number of oxygens for the second row elements, and we're dealing with groups 3 to 6 technically, we use the bottom portion of the table. So we'll call the first one borate, the next one carbonate, and the next one nitrate, because they have the maximum number of oxygens, right? So we go with the first row. And then for nitrogen, where you can have one less oxygen, we just move on to the next row in the table, and that will be nitrite. Alright, now let's take a look at the elements in the third row, basically anything below the second row of the periodic table. Let's look at groups 5 and 6. Okay, so we'll be looking at phosphorus, arsenic, antimony, and we will be looking at sulfur, selenium, and tellurium. Alright, because these elements are below the second row, automatically they have 4 oxygens as the maximum value, and the charge is given by group number minus 8. Alright, so let's take a look. Also, because we're dealing with groups 5 and 6, we have to restrict ourselves to using the bottom portion of the nomenclature table. Alright, so for the maximum number of oxygens, which is 4, and the charge, which is given by group number minus 8, if you're in group 5, 5 minus 8 will tell you that the charge is minus 3. And if you're in group 6, 6 minus 8 will tell you that the charge ought to be minus 2. So all we're going to do now is just input the name or the element symbol for groups 5. So that will be phosphorus, arsenic, and antimony, P, AS, and SB. And for group 6, we'll have sulfur, selenium, and tellurium. So the symbols will be S, Se, and Te. The maximum number of oxygens will be 4 since we're below the second row. And the charges we just calculated with group number -8. 3 minus for all of the group 5 analogs, and 2 minus for all the group 6 analogs. Now, because each one of them has the maximum number of oxygens, they will all be called with the ending ATE. The first one will be called phosphate. SO4 2- will have to be called sulfate, arsenate, selenate, antimonate, tellurate. If we decrease number of oxygens by 1, then we move on to the next part of the row, which is ITE, not to be confused with IDE. ITE implies that you're dealing with a polyatomic ion. Okay, so for them, you basically do the same, you follow the same approach. Start with the name of the central element, followed by the ending. So phosphite, sulfite, arsenite, selenite, antimonite, tellurite, simply by decreasing the number of oxygens down to 3. And in the case of phosphorus, you could actually go down to 2 oxygens, which is decreasing the maximum value by 2, so you end up with hypoite or hypophosphite. Alright, now group 7. We're going to use the top portion of the nomenclature table to name these particular anions. And since we're dealing with group 7, 7 minus 8 will give you a charge of -1 for each one of these ions. Since we're going to be below the second row, starting with chlorine, we gotta have 4 oxygens to begin with. So we have 4 oxygens for chlorine, 4 oxygens for bromine, 4 oxygens for iodine, and all of them have the 1 minus charge because we're in group 7, meaning 7 minus 8 is -1. Alright, so decrease number of oxygens from 4 to 3, from 3 to 2, and from 2 to 1. 4, 3, 2, 1, 4, 3, 2, 1. And simply follow the table. Maximum number of oxygens per 8. So that means that the first one will be per chlorate, per bromate, per iodate, followed by the next number, which ought to be 8, so chlorate, then chlorite, then hypochlorite. And the same trend applies to the bromine analogs, per bromate, bromate, bromite, hypobromite, per iodate, iodate, iodite, hypoiodite, just by following the table here on the left side. Alright, now let's bring everything together and see how this goes. And here goes an example that's similar to the one we did before. When we were dealing with the binary compounds, I gave you Lec4 sulfide as the example. But this is Lec4 sulfite. And that implies that this is a polyatomic compound. First of all, we have lead with a 4+ charge. So we can write that down. Now sulfite, in order to determine what that is, we have to take a look at the table. As of now, because this ends with ITE, and the same thing would have been true if it ended with ATE, we know that we have to have oxygen present in the anion. What we don't know right now is the number of oxygens or the charge of the anion. However, if you look at where sulfur lies, two things to notice. First of all, this is in group 6. That's going to allow us to determine the charge of the anion, but it also lies in row 3, so that's below the second row. And what that tells us is that the maximum number of oxygens that it could have is 4. Alright, now because you're dealing with group 6, we deal with the bottom portion of the nomenclature table. Maximum number of oxygens, 8. 1 less than that, ite. 2 less than that, hypoite. Now the name ends specifically with ite. This is sulfite. So that means that we're going to be dealing with 1 less oxygen than the maximum, and the maximum is 4. Therefore, we are end up with only 3 oxygens in this structure. Alright, so that's how we figure out how many oxygens we're dealing with. Now for the charge, you will once again use group number -8. And the group number of sulfur is 6. 6 minus 8 is -2, so now we know the charge of sulfite. And at this point you do the same thing we did before. You use the charges to come up with the proportions. You simply cross multiply the amounts. The 4 goes in front of the sulfite, and notice the use of parentheses to symbolize that the 4 applies to the SO3 unit altogether, not just the sulfur. Excuse me, not just the oxygen. And then the 2 that was the charge of sulfite, comes in front of lead. At this point, don't forget to go with the lowest multiple, so that you basically divide both sides by 2 and end up with PB parentheses SO3 parentheses 2. And that will be how you derive the name and the formula of the structure. All right, now there's one additional factor that needs to be discussed. Sometimes, especially for anions that have a high negative charge, you could have hydrogen present in the structure and still have an overall negative charge. Now, what you're going to have to keep in mind is that hydrogen bears a positive charge for every single hydrogen that you have present. So this is what happens. Phosphorus is in group 5. It's below this second row, so you can have a total of oxygen atoms equal to 4. So for 4 oxygens, the ending is 8. So this thing here will be called phosphate, right? And the fact that the group number minus 8, group number of phosphorus is 5, is negative 3. For you to have that negative 3 charge means that you have no hydrogens present. Okay, but this is phosphate. Now, if you start adding hydrogens, what ends up happening is that the charge decreases. And I'm going to present you with a formula that will incorporate that in the picture. So notice that with one hydrogen, the charge is now 2 minus. With 2 hydrogens, the charge is minus 1. And that's because the formula needs to be augmented somewhat. Basically, you just have group number minus 8 plus the number of H's present. And so this is the updated version of the equation. Notice that for the one hydrogen here, we'll have, okay, group number for phosphorus is 5. 5 minus 8 is minus 3, plus the one hydrogen, that will give us the minus 2 charge. And over here, where we have 2 hydrogens, group number of phosphorus is 5. 5 minus 8 is minus 3. Minus 3 plus 2 hydrogens is minus 1. So the way you basically name them is by specifying how many hydrogens the anion has. Yes. So the first one only has one hydrogen, so we call it hydrogen phosphate. The second one has 2 hydrogens, so we call it dihydrogen phosphate. And if you were to add one more hydrogen, well, what you find out is that the charge fully cancels out because you have 5 minus 8, which is minus 3, plus 3 hydrogens will be 0, so you end up with H3PO4. And the one thing that you need to be careful about is that this compound should not be called trihydrogen phosphate. And the reason why is because it doesn't have a negative charge. The negative charge is gone. We use the ATE ending because these particular examples were anions, but this one is not an anion, it's a neutral compound that starts with an H. And because of that, this is an oxyacid. It's molecular. So you gotta revert back to using ic acid. So it's not trihydrogen phosphate, it's actually phosphoric acid. In other words, you take the ATE ending and replace it with ic acid again. So just be aware of those little, tiny little details. They're going to be important to keep in mind. But all right, with all of this, we finished talking about nomenclature. We'll have to do plenty of examples during discussions and during office hours, because this will take plenty of practice on your part to get it all down. As you saw, the rules are not particularly difficult, but they do require a certain level of memory and a certain level of dedication and practice to fully get it down and understand it. So, I look forward to those particular exercises in the future. So, with that being said, see you in the next lecture video.